All right, this is the AC Circuits Lab. AC Circuits Lab. And so we don't want to hook the AC power supply up to anything other than the digital multimeter right there. So we have it set up to measure voltage, and we want this cranked up all the way. And so using the digital multimeter, measure the AC. I had to switch out multimeters because that last one had an issue. All right, so we have the two sides here. They're both the same color in terms of what's coming out of the box here, because there is no automatic high side and low side like there is for DC. This is always the high side for DC and always the low side for DC. For AC, it flips back and forth. That's the alternating of alternating current. For the sake of this, and it's going to make a difference later, I'm going to assume that the right side is the high side and this is the low side. That'll make a difference when we're trying to make sure we have phases correct. Otherwise, we could be 180 degrees off or pi radians off, and that will have serious consequences for our results. So we're going to start out with trying to set up this for the digital multimeter here. There's the multimeter. Again, I have my high side set into here, onto the high side of the probe, and then the low side of the probe, the thing that's marked common, marked to what I'm going to consider the low side of the power supply. I'm going to turn it on, and it is oscillating back and forth, and so the multimeter, though, is measuring a single value there. Again, that's not the peak, but that's one of the questions I'm going to ask you, but 3.9, looks like it's stabilizing at 1, and there it is. So I'm going to turn that off, and you should record that number. The maximum current that the probe and the resistor box can handle, this is the resistor box right here, and the maximum is printed right there. That's the maximum. The current probe, it is printed also directly on there. Their maximum current that it can handle is printed right there. I believe I have set this to within that 10 to 20 range. What happens if we actually exceed the current is that you start to smell burning plastic, and I've done that before on some of these, and some of these that it burns what's inside. So I'm trying to definitely avoid that. And so I think I've set it within the proper range there. And the actual resistance that is set is, of course it won't stay still. Notice that is 0.8 for 3 at the moment, kilo ohms or 843 ohms. And so that is the measured resistance. And so we're about to find current, just a second. I want the voltage to be AC voltage to be between 3.8 and 4.2, so 3.8 and 4.2 volts, and right now I'm at 3.83. I'll crank it up just a little bit if we want, hopefully not too far. So 4.1 to, look at the video and determine for yourself what number that should end up being. So there, we are definitely within that range right there. And so we have satisfied those pieces. Excellent. At this point, we're going to leave this dial the same. We should not touch that dial at all. If we do, we're basically have to start from scratch. So I basically turn it on, and so current is flowing through here and then back. That's sort of the path that I'm taking. We need to measure the voltage across the power supply and the resistor, and so I am going to do that. I'm going to try to set this up so that it just doesn't want to do it that way. So I grab some wires here. I've got my probe here, and I've got my one here. So first thing I do is I measure the across this. There we go. And I want to measure, that is the voltage across the power supply. So this is what it's measuring right now. Very similar to what we had before. It could be just a fluctuation. Now I want to do it across the resistor. So I take my probe and into here. Now we're measuring the voltage across the resistor, and that is the voltage that we were getting there. It is the same number as we had going across the power supply just now, and so that's good. It should be. All right, now setting up for the current. The current here, let's turn that off. Just make sure that we're set it up right. So we have basically currents flowing out of here, and again, I'm assuming that's the high side, current flowing out of here through the multimeter and then into, and then following the wire around, then into the resistor, and then out of the resistor back to the power supply. Now again, it's going to be flipping back and forth the direction. However, in terms of conceptually, just trying to realize which way, have some sense of which way it's going. The current I would expect to be in the milliamp range. So I put that on milliamp. I click on AC, and then I turn this on. And we have 4.94. As registered by the DMM. And then if we actually do the calculation here, then it should be roughly 4.17 divided by 843, and 4.95 is what calculated theoretically, and that is, let's go back over here. Notice that is milliamps there. So make sure it's marked accordingly on the paper. And I'm going to stop until we set up for the next bit. So now we're going to make sure that the current probe is, we're using current probe instead of the digital multimeter. And so again, I'm assuming this is the high side right here. Current flows through here, through into the multimeter in this direction right here. And again, that makes a difference, and I'm connecting this side with this side right here. I need to be consistent however I do it. And then out this side, through the wire, into the resistor, from resistor back into the power supply. When I do the multimeter, I'm going to be setting up, basically going to this table right here. And the first one is 10 samples a second. And so I need to change from my 10,000, because I haven't, the 10,000 comes from the previous lab that I just recorded, into 10 samples a second. And I want a duration of 60 seconds. And then click OK. And now I'm going to turn this on. So power supply is turned on, and I'm going to start the recording. So we have a relatively simple pattern right here. It will look like there is some sort of pattern in the long run here. And, instead of letting it run for 60 seconds, I'm going to stop the video, and then I'm going to come back after the pattern has been established. So after 60 seconds, this is what it looks like. It looks like there is a pattern there. It doesn't always it doesn't always look like this, but there's something underlying here that is hidden at the moment. And if we go to graph options, and I want to change the domain, instead of 60 there, I want 0.16. Done. And take a look at the graph now. That's basically what it looks like. So that's the domain 2 that I talk about in table 1. We're going to run it again, except this time we're going to go 50 samples a second for 30 seconds. So if there's a pattern, we should get a little bit of clarity there on the previous one. So let's go to here. Change the sampling rate to 50. Okay. And then let's run it again. Oop. Let's cancel, because I also want 30 seconds. You can do it for 60 seconds. There's not a harm in that. It's just that doesn't really provide a significant amount of detail there. So discard. And so now we're going to go for 30 seconds. And we went from what looked like a relatively clear pattern to this mess here. And this is exactly what I would expect for 50. We will let it run. Go ahead and let it run the 30 seconds. All right, so that's the 30 seconds. Let's go ahead and zoom into the point, change the domain to get domain 2. Nope, graph options. Change that to 0.16. And we start to see a little bit more of a pattern. And this is actually significant. There is a reason why you didn't see it on the first one. I think it's one of the analysis questions. And so let's now go back to this one. We're going to do 60 samples a second and 60 seconds. So change that to 60. And change this to 60. We're going to run this. Okay. And then run, discard. All right. So now we start to see something showing up again here. I am going to stop this and then come back after the 60 seconds is up. All right, the 60 seconds is up on this trial right here, and this was the 60 samples a second. It is, again, it looks like a pattern here. If we zoom in to graph options, and again, 0.16 seconds, because that's what the table 1 asks for, or for what they ask. Done. Okay. It doesn't look like as much of a pattern there as you would potentially have thought. Now 120 is not on here anymore. I'm going to do 120 anyway, just to see what shows. Actually, I'm going to do 100 just to see what shows up. So let's go back over here and 100 samples a second, and let's do that for 30 seconds. All right, again, it looks like more of a mess, but when we zoom in, it should be less of a mess. And 30 seconds are up there. So now let's go to graph options, zoom in to 0.16. We see what kind of looks like a pattern there. It is up and down as you would expect. And so what I'm going to do is, again, let's do 200. 200 is not on the chart, on the table there, but let's do it anyway. Actually, let's do 120 first. And let's keep it at 30 seconds. That's what the first 0.16 seconds goes. Notice that there is definitely a rhythmic pattern there. So it's recording more data than what it's showing right now. We're sort of doing it in reverse order. And we're a little more than halfway, about 10 seconds to go. I'm looking at the lower right-hand corner. And done. And then if we go to graph options, auto scale. Wow, we get that. That seems odd. So now let's do 200 samples a second. Again, we're only doing this for 30 seconds. As it builds, it looks like a big blur there. And then if we zoom in, actually, let's see if we can do it this way. Graph, zoom in. Notice we start to see something a little bit that's looking more like a pattern here. Zoom in again. We are seeing something here. So now let's get back to the table, 480. Because 480 is so many samples, if we actually ran it for 30 seconds, it would overwhelm the machine. So let's change this to just 0.16. Discard. Oops. That did not work well because the circuit became undone. The clip fell off the resistor. So let's try that again. And we're seeing something more so here. That's 480 samples a second. And let's do it again for 1,000 samples a second. and 0.08 seconds. And now we actually see the pattern that was underlying underneath it all. That is rather major right there, and I believe we actually need to keep that. We're going to keep 1,000 samples a second for the rest of the lab. And all right, I'm going to stop it here while I set up for the next part. So I have this thing hooked up now. Got a lot more wires involved here. I've got 3 different probes going, as you can see right there. 2 are potential probes and one's a current probe. We have current flowing out of, again, I'm assuming this is the high side. So current flows out of here through the current probe, and then through the wires into the resistor, out of the resistor, and then into here. So when I hook up the differential voltage probes, I want to make sure that the high side on the voltage probe matches the high side of the voltage. And so right here, this is one of the voltage probe. This is the one in slot 1. That's the red one right there. I put the red lead on the high, what I'm calling the high side, and the black lead on the low side. And if that's the high side, again, current flowing from that side. And over here, this would be the high side of the resistor, and I have that on the high side and the black on the low side. So now they should be in phase. We'll know very quickly if I've set that up correctly or if something has gone strangely wrong there. And it should, oh, when I changed it, the rate changed here, so I want 1,000 samples a second. And I definitely don't want 18 seconds, I want 0.08 seconds. And okay, and then let's run it. All right, so a whole bunch of stuff is showing up right there, and I really want to only look at one at a time. And so what I'm going to do is I'm going to go to graph, show graph 1, and those are the potentials. All right, something, oh, duh, I forgot to turn it on. All right, so let's turn it on. Let that focus, and then there we go. There we go, that's what I want. All right, that is 2 potential graphs, right? One on top of the other because they are in phase. And if we actually showed all 3, so graph, show graph, all graphs, notice that they peak at the same spot. So this is the current probe right here, and this is there are 2 voltage probes right there. They are peaking at the same place. That means that they are in phase, which is what I would expect for a resistor. Now we need to know we need to be able to get the equations here in step 10. And so analyze, curve fit. This is the slope for, this is the first one. This is the power supply. And I want to do a cosine curve. Now notice that the black line goes over what we want here. That is good. And there are the values right there. The 5.8801 is the amplitude. The 377.01 is the angular frequency. The 3.5314 is the phase shift. And D is how far off of 0 it is. Ideally, that would be 0. And the RMSE is, I guess I don't actually ask you to record the RMSE. The important thing is when you visually inspect it, that the black line is on top of the red line. Now let's do the same thing for the next one. So let's hit cancel. And so analyze, curve fit, the second potential. This is the one for the resistor. Again, I want to do a cosine curve. And there you are. The amplitude is about the same, if not the same. I can't remember the exact number. Definitely, the numbers are roughly the same as what they were before. D is a little bit off, but that doesn't really matter. That's, again, dealing with how much it has or has not been zeroed. And now for the current, I would expect the amplitude to be different for current because it's on a different scale. Analyze, curve fit, current, and again I want to do a cosine curve. Amplitude is different as expected, but I would expect B and C to be roughly the same. So B is the angular frequency and C is the phase shift. All right. And then you have the three angular frequencies, which will average together for the experimental, and then it asks you to sketch it. So when you do the sketch, please make sure that it's clear which one is which. They do not have to be on the same scale. I'm looking for a rough sketch. I mean, so basically what I would expect is you got 1, 2, 3, 4, 5 peaks, and you know, basically you have roughly 5 waves there. So that's sort of what I'm expecting to see within the 0.0. Oh, I actually, in there, I wanted 0.04 seconds, so let's cancel. Graph options, change that to 0.04. There you go. So that's roughly what I'm expecting to see in terms of the sketching of the graph. All right, I'm going to turn this off and set up for the next part. All right, so this is the next part. So we're dealing with a capacitor. This is known as a capacitance box here, or they call it capacitance substitution. I can turn the power supply off for right now. So this is the high side and the low side of the capacitor, and so I have, so I set it up as such. So I have the wire coming from here through the current probe, from the current probe, wrapping around into the high side here, and then from the low side back into the power supply down here. So we should know very quickly if it's set up right or not. And so let's turn that on. And we're going to basically run for 0.04 seconds. Just let's confirm we're still doing 10,000 samples a second and 0.04 seconds. So let's run it. Flower pattern. And so notice now the current is now out of sync with the potential or the voltage. So those are now out of sync as is expected. Remember the Iceman, the current comes before the voltage. So to do the equations, it's also sort of jaggedy, but that should not affect our overall value here. So first the potential, cosine curve. And there we have the values right there. Notice that the angular frequency is still about the same. The amplitude is still about the same. And the phase is going to be different because that depends on what time I actually start the thing. So we have a phase of 0.49122. Let's go to the next one. So now analyze curve fit the second potential. And again, cosine curve. And so again, amplitude about the same, the angular frequency about the same, C, the phase shift, 0.49604, I forget what the other one was, but hopefully it's somewhere around there. Notice that is in radians, by the way. And so now the current should lead by pi over 2. And so what I would expect is, see, this is 0.49604 is this phase shift, and then pi over 2. I expect the phase shift of the current to be roughly 2.067. So now let's do analyze, curve fit, current, cosine. And I said 2.067, it's 2.029, so pretty darn close. Amplitude, of course, is much smaller. The angular frequency, 381, is a little bit elevated, but you know, for someone its age, that's the kind of thing that happens. And then you would do the sketch, and you saw the pictures before. All right, so part C. Now part C and D would be really nice if we could do it all at once, but part C and D, we would really need one more outlet. So we only have three docking right here, so we're going to do current and 2 voltages to start with, or sorry, we're going to do 3 voltages to start with, and then we'll do the current after we do a little bit of shifting. So I'm going to turn this off and set up for part C. All right, so the setup for this one right here, I have none of the probes or sensors set up right now. Again, imagining this to be the high side, the current flows out of here into the resistor, across the resistor, through this wire into the capacitor, and then from the capacitor back into the power supply. So that's the basic setup right there. I'm now going to set up the 3 voltage probes. The first one's going to be connected to the power supply, the second one will be connected to the resistor, and the third one will be connected to the capacitor, just as is written right in here. So I'm going to turn this off and then come back. All right, so I've just put in the first one right now. So that is in channel number 1. That is the voltage probe. That is hooked into the power supply. And again, I'm assuming that this is the high side and that is the low side, so that's why I have the red connected here. So since the current is going to be flowing across there into this resistor here, I'm considering this the high side of the resistor, and that's the low side of the resistor, and then high side of the capacitor, low side of the capacitor, and then back. So I'm going to set up the other 2 now and then come back. I now have it set up. So I've got my voltage probe here, I have my voltage probes here, and my voltage probes here. So now when I run it, they should actually be out of sync as we did this actually. This is the RC series circuit, we did it already. So run it for 4 seconds there. It would help to actually turn this on, and so let's run it again. And all right, so we have the 3 graphs here. So the blue one here is the power supply. I know the current's the same through all of them, so I would expect the voltage for since the current leads the voltage of the capacitor, I expect the capacitor to lag, and therefore the red one, which is the third one, which is the one hooked into the capacitor, that's the capacitor. Yeah, that's voltage across the capacitor, and the leading one is the one across the resistor. If we did current, which on the next part, we'll do current, but there they are. Those are in the order that I would expect. And so analyze, curve fit, potential. This is the third one. So this is for the voltage across the capacitor. And there are the numbers right there. And so now let's do it for the next one. So analyze, curve fit. This is for the first one. This is for the power supply. And there are the numbers there. And now cancel and do it for curve fit for the resistor, which is the second one. And there are the numbers there. And while we're here, all right, let's just take one particular point right there. We have the voltages, the 3 voltages at this time of 0.021 seconds. Notice that if we add the potential for the capacitor plus the potential for the resistor, so 1.727, 3.151 negative, we end up with negative 1.424 and it's coming out at negative 1.535. Let's see how close we get at another point. Let's just pick that point. And again, the capacitor plus the resistor should give us the potential for the power supply. So 3.505 negative, 2.390 plus, and we're off by about a little under 0.2 volts. It is physics after all. but it would have been nice if that had worked beautifully. All right, so I'm going to take this apart and set this up for part D. All right, so basically we've taken out the voltage probe across the capacitor and put in the current probe. And just to make sure we've set up correctly, again, assuming this is the high side right here, the current's going to flow down here into the resistor, so this should be the high side of the resistor, thus this one's red also. It goes through the resistor coming out here, and then it's going to flow on into the high side of the capacitor. And then from the low side of the capacitor, it's going to then go through our current in the direction that we were making that assumption, and then back into here. And the reason this makes a difference is the phase definitely becomes critical here. Now, I am expecting that the current should be in phase with the resistor. And well, actually, yeah. So let's go ahead and run it and see what happens. So, oh, I never turned it off. Okay. All right. So we have the current probe. Notice that the peak here at the current, the red line here is peaking about the same time as the resistance is. Resistance in channel 2. Channel 1 is the power supply. Let's do our curve fits here. Analyze, curve fit. This is the, cancel, let's make sure I got that. Yeah, that's the power supply there. Curve fit. So voltage across the power supply. Do a cosine curve, and there are the numbers. Then cancel, analyze, curve fit, and this is for the resistor. And then cancel, and this is for the current. And that is for the current. All right, and I think there we have it. The rest of it is just analysis and sketching, and so I hope you had fun. I know there are a lot of wires, a lot of tangling around, but it is satisfying to get some of the results that we get for this.